In this video, we're going to take a look at our kinematic relationships between position, velocity, acceleration, and time, but using graphical methods. So far, we've mostly talked about equations to get our kinematic equations that we're working with between these four variables. But there may be times where a graphical method, some kind of visual representation with an axis of position versus time, or velocity versus time, acceleration versus time, any of these can be really helpful, especially if the motion is changing, if you have some kind of constant state of motion that then changes. So we've been discussing those relationships between velocity, acceleration, and position. And one of the main ways that we've represented those is through the formulas of derivation and integration, where we say our acceleration, for example, is the derivative of velocity with respect to time. And we can use that as a way to get between these things. We could rewrite this also as our change in velocity is the integral of acceleration with respect to time. We can use the same idea to go between velocity and position, right? Our velocity is just the derivative of position with respect to time, or our change in position is the integral of velocity with respect to time. So the reason I bring these up is because it's really more of a calculus review that we're kind of talking about right now, right? We're going to be talking about these graphical methods where if you're given, say, a graph of position versus time, you can get to a graph of velocity versus time or a graph of acceleration versus time, right? And the way that we do those, since we're taking a derivative of, say, some, S versus t graph, all we're doing is taking the derivative of that. And our calculus reminder here is that a derivative is really just a slope. The slope of that line at any point, so you have positive, 0 goes negative, the slope of that line is what translates into the points on our v versus t graph. And again, we take another derivative. Taking derivative of velocity is going to give us acceleration. So we can take another derivative where we have, now my acceleration's a little off, but our acceleration takes the slopes from the v versus t graph, getting negative, more and more negative, so it's negative and more negative on our acceleration graph, right? Just taking the slopes from those functions to take derivatives up to acceleration. And it works in the opposite fashion, right? I can find the area under the curve of my acceleration graph in order to find my velocity and plot those velocity points. I can find the area under the curve for my velocity graph to find my position graph. Right? So I can go between these graphically knowing that derivatives give me slopes and integrals come from area under the curve. And I can use these relationships to go between these in cases of erratic motion. So let's take a look at a couple of examples. In our first example, we have a bicycle that moves along a straight road such that its position is described by the graph below. We want to construct the VT, so velocity versus time, AT, which is acceleration versus time graphs for 0 to t to 30 seconds. So if we look at this graph over here, we can see that on our bottom axis, we have our t-axis, our time going from 0 to 30 seconds. But notice that we have this break at 10 seconds here. This break at 10 seconds, because our function is changing. We have one s function, s equals t squared from 0 to 10 seconds, and then we have another s function from 10 to 30 seconds. S is 20t minus 100. So because we have these two different s functions for these two different sections of time, we're going to need to account for them differently and keep that in mind when we're constructing our v and our a graphs. So for our v graph, if we remember, our velocity is just the derivative of s with respect to time. Again, the big key here is just to remember we have to do this twice. For our first time interval between 0 to 10 seconds, and our second time interval with the other function between 10 and 30 seconds. And all we're going to do is take the derivative of that s function. So in our first section, our s is t squared. Our velocity, since it's the derivative of s with respect to time, is going to be 2t. That's the function that we're going to be plotting from 0 to 10 on our vt graph. We can go ahead and do that. We can go ahead and say, let's just put our little graph down here, velocity, time. And so our first section from 0 to 10 is 2t. 2t. So at 0, I know that it's 0, and if I plug in the end of the interval 10, times 10 is 20. This goes from 0 to 20 high in that 10-second time period. So that's our first part of the graph. Now we'll need that other part of the graph that goes all the way out to 30 seconds. So our s for our second part of the graph, 20t minus 100. We take the derivative of this function to get velocity. We'll just have v is 20. So v is just a constant 20 between 10 seconds and 30 seconds. Easy enough, we can plot that on our graph, just a constant 20. A constant straight line at 20. And that's it. That's all we have to do when we're going between these graphs. We just take our derivatives or take our integrals, depending on what we're being asked, and then we're going to plot them. So we can do the same thing with our acceleration. Right? Our acceleration is just the derivative of velocity with respect to time. So we can take each of these one step further. Move this vt graph to the side here. We'll make ourselves an AT graph. So acceleration versus time. And we still have those two time intervals because we have different velocities. So from 0 to 10, 0 to 10, 10, 10, pretend that says 10, I don't know why that's not working. And then from 10 to 30. We can take our derivative of our velocity functions now. So derivative of 2t gives us an acceleration from 0 to 10 is going to just be 2. For our second half, from 10 to 30 seconds, the derivative of velocity of 20, derivative of 20 is a constant, so the derivative is just 0. There's actually no acceleration from 10 to 30 seconds. So that one's really easy to draw, right? We have our constant acceleration at 2. And then at 10 seconds, that drops down to 0. No acceleration between 10 and 30 seconds. And that's it. Those are our graphs, right? We could take these area underneath the curves to get back to our original function. But this is all we're being asked to do. We're being asked to plot these relationships, just remembering that graphically there is significance, there is a meaning between these relationships for position, velocity, acceleration, and time. But let's go ahead and take a look at another example. This example that we have is going to be a little bit different from our last example because as we can see from our graph that we're actually given velocity versus position instead of versus time. So our setup for this one is that our VS graph describes the motion of a motorcycle, and we want to construct the AS graph of the motion and determine the time needed for the motorcycle to reach a position of 400 feet. So we've got our graph over here. Let's go ahead and start with constructing that AS graph. And if we remember, we do have another relationship between position, velocity, and acceleration that doesn't involve time at all. And so that was A equals dv ds times v. A equals velocity times the derivative of velocity with respect to position. So what that means is we can plug in these things from our functions from our graph on the left to find, for these two intervals, to find that acceleration function that we want to get to plot. If I go ahead and look, just like in our last problem, we have these two intervals. We can see we have an interval from 0 to 200, and then again from 200 to 400. Again, we're looking at now a position, but still with two separate intervals to look at from that graph on the left. Again, we have our velocity, so let's go ahead, we're going to go work through this entire left portion first. This velocity is 2s plus 10. 2s, oops, that looks bad, let's undo that. 2s plus 10. The velocity is 0.2 times s plus 10. If I want to find dv ds to plug into that acceleration function, dv ds, the derivative of that velocity function with respect to s. So in this case, just going to be 0.2. And I can use these two things, plug them into our original equation up here, get acceleration equals dv ds, we just decided is 0.2, times the velocity, and that velocity function is 0.2s plus 10. So the function I have for s from 0 to 200 for that interval is going to be 0.04s plus 2. And we'll plot that in just a minute, but let's go ahead and do our other side here, our other function from 200 to 400. There we're given that v is a constant. V is 50 feet per second. So since v is 50, the derivative of v with respect to s is just 0, right? Constant velocity, we should know, means no acceleration. No acceleration. So even if you don't intuitively know, it's not quite in your brain yet that constant velocity always means no acceleration, at least in the direction of travel. Then when you take this derivative, it should be clear, right? You take the derivative of velocity, gives you a 0. If you plug it into the formula, you get an acceleration of 0. So that when we go to plot this, it's up just a little bit so we can draw this plot of A versus S. This is the graph we're constructing, exact same bottom axis. We're going to go from 0 to 200 and from 200 to 400. And we're going to plug these in. So if I plug in 0, that's my lower bound for my left side, into this acceleration equation, I'm going to get 2. So it starts at 2, and if I plug in my upper bound of 200, I'm going to get 10. I have this linear, we can tell it's linear because it's 0.04s, no squares, nothing else. From 2 to 10 linear up to 200. And then at 200, my acceleration drops down to 0. Drops down to 0. No acceleration from 200 to 400. And that's it. That's all I have to do. Really, the hard part is remembering this relationship between acceleration, velocity, and position. But once we have that, it's really just a matter of taking that integral. And that gives us our AS graph. Now we did have one more thing we needed to find here. We needed to find the time needed for the motorcycle to reach a position of 400 feet. Time needed to reach a position of 400 feet. So we're given these velocity functions. We want to find a time, and we're given the position. So with all of those ingredients, if we can think of an equation to relate those things together, then we can get somewhere. Right? Something to relate position, velocity, and time. And thankfully, we have one. Go ahead and I'm going to delete all of this out. we're going to look at how we get that time. Right, so that relationship between position, velocity, and time is going to be our velocity is ds over dt. And if we rearrange this, dt is ds over velocity, over that velocity. So that when I integrate this function, I get the integral from 0 to t for my dt, and the integral from 0 to 400, right? That's the entire position span that I'm going. I'm moving from 0 to the 400 for my ds over v. Now that way I can solve for time from 0 to 400 ds over v. And I kept it as that 0 to 400 ds over v because we're actually going to have to split this guy up. Because if we remember these functions over here, we have two different velocity functions. Two different velocity functions that have to be plugged into this integral. So actually what we have is not from 0 to 400, but we're going to be doing one from 0 to 200 to represent the first velocity function, and then again from 200 to 400 for that second velocity function. So from 0 to 200, that amount of time, again, integral from 0 to 200 now, is ds over the velocity function for that section. So that's 0.2 s plus 10. Whereas our 200 to 400 segment, the time for that is going to be from 200 to 400 ds over our velocity, which there is a constant 50. There's just a constant 50. So these two velocity functions, or two time functions now that we have, that we're going to need to calculate individually and then add together to get a total time. So let's go ahead, let's do this right one first. It's a little bit easier, that one with the constant velocity of 50. If I integrate 1 over 50 times ds, I'm just going to get 1 over 50 times s. Right, this is 1 over 50 s evaluated from 400 or from 200 to 400. So I plug those in. 1 over 50 times 400 minus 200 is going to give me a time of 4 seconds. Easy enough. Now we can move on to our integral that's a little more complicated, a little bit more work. Because if we don't remember all of our special skills from calculus, this is a very special integral. 1, we're going to have to use a u substitution, and 2, it is itself a special integral when we take that integral. So we can't just integrate this 0.2s plus 10 function. We're going to have to use a u substitution for this, where our u is going to be 0.2s plus 10, and if we take the derivative of this, du is going to be 0.2 s. So du over 0.2 equals ds, and then we're going to substitute this in. That's going to give us our integral of now ds is substituted in, so du over 0.2, and that u gets substituted in for the bottom there, times u. So now we can take this integral. I'm going to go ahead and take this 0.2 out, so 1 over 0.2 gives us 5. So 5, and that leaves us with integral du over u, which again, this is a special integral, right? Our integral of 1 over x is natural log of x. When we integrate this guy, he's going to be 5 natural log of u. And sometimes you can put absolute value of u, you can put parentheses of u. I know math teachers are really a stickler about making that natural log an absolute value, But in our case, when we go and put this u back in and evaluate, I plug back in 5 times natural log 0.2 s plus 10. We're evaluating that from 0 to 200. Really, I don't need those absolute value signs there because everything inside of there is going to be positive. It's a definite integral. I know exactly what I'm plugging in. I don't need it because my s is going to be positive. Looking at my graph, I'm only dealing with positive s's. So I can plug those into my calculator and I can get that time of about 8 seconds. 8.05 seconds. So for that first position, going from 0 to 200 feet took about 8 seconds. Then going the next 200 feet, 200 to 400, only takes 4 seconds. So in total, the total amount of time it takes to reach position 400 feet is just adding them together. So 8 plus 4, about 12 seconds for the motorcycle to reach a position of 400. Do one last example. Here's our last example that we'll look at for today. And again, I want you to go ahead and pause this video. Go ahead and try it for yourself before we work through it together. So it says a rocket car starts from rest and travels along a straight track such that it accelerates at a constant rate for 10 seconds, then decelerates at a constant rate. Draw the VT and ST graphs and determine the time needed to stop the car. How far has the car traveled? Again, go ahead and pause this. We'll take a short break. Try to figure it out on your own, and then you can come back and see if you got the right answer. And we'll work through it together. All right, so we have our rocket car. He's going initially at 10 meters per second squared. That's his acceleration, a constant acceleration. And then we can see he drops down to -2 meters per second squared. But the big scary thing that most people might get stuck on here is that we don't know what this ending time is. But the key to this question really lies in the wording. We have to pay really close attention to everything that our question is telling us. We know we need to find the VT and ST graphs, but one of the most important things this question tells us, which it starts from rest to accelerate. Oh, well, okay, I thought it told us that it comes to a stop. It accelerates, decelerates at a constant rate. Oh, time needed to stop the car. Yep, it is there. Sorry, thought I was going crazy. It is there. So we want to know how long it takes to stop the car. So we're accelerating at first. We start from rest, we accelerate, and then we decelerate to come back to rest. So it's telling us that our initial velocity and our final velocity conditions are going to be 0. Those things we do know. So when we go to make this graph, go ahead and set up this VT graph. And to get to velocity from our acceleration, it's going to be an integral. We know that relationship. The integral of a dt is what gives us velocity. And integrals are just areas under the curve. So we can calculate that first area under the curve. Right? This 10 times 10 gives us area 1. That's going to be 100 meters per second. And so what that means is that's what it is at time t, right? At this end time, 10 seconds. Because we know that initial velocity is 0. So we're starting from an initial velocity of 0. Car starts from rest, as the problem statement tells us. And then it goes up to 100 meters per second in those first 10 seconds. So it has a velocity of 100 meters per second. In those 10 seconds, linear, because our acceleration was constant, gives us a linear velocity, right? If you think about this as an equation, you can think about it as acceleration equals 10. When you integrate that, you get a velocity of 10t. So when you plug in 10 seconds, you get a velocity of 100 meters per second. That's where these numbers are coming from. And then we see, okay, now we have an acceleration of -2. Acceleration of -2. And so we know the slope of that line. We know that it's going to be -2. So it's going to be a lot gentler, a lot less of a slope. B equals -2t. And we know that it has to come back down to 0. Right? So we know that this A2, in order to come back down, A2 and A1 have to be equal. If it's going up to 100 meters per second, then it has to come back down to 0. So we know that A2 is also going to be 100, where that's going to be -2 times t equals 100. So that change in time there is going to be 50 seconds. And again, that's 50 seconds from the 10-second mark. 50 seconds from the 10-second mark, which means we need to add on those original 10 seconds. Right? That's our starting. So t, the end here, is actually 60. Makes it 60 seconds to go back down to 0. So this is our velocity versus time graph. This is how we get the total time needed to stop the car of 60 seconds. Right? What goes up must come down according to this problem statement. And then we also need our ST graph and finding out how far the car has traveled. So again, we're going to go through our same process, although now we know our time intervals. We know 10 seconds from 0 to 10 and from 10 to 60 are our 2 time intervals. And again, we're just taking integrations. We're just finding those areas under the curve. Where if I find this area here, from my 0 to 10, area under this triangle is going to be 1/2 base times height. Area of a triangle, 1/2 base times height. 1/2 base, I go from 0 to 10, so that gives me 10, and then the height of that triangle is 100. So that tells me that my initial position, we're at 0, and my final position is represented by this area under the curve. So that's going to be 1/2 times 10, that's 5, times 100 is 500. Is 500. And we'll notice my slope is getting higher and higher and higher, right? When I integrate, the number on this line represents how steep the slope is. So here, the number on my line is lower, I have a smaller slope, and then the slope gets larger and larger and larger. Until I get to 10 seconds, that's the largest it is, it's 100. And I can do the same for the come back down. Right, area under the curve, 1/2 base, this time my base is 50. Right, that's the 60 minus 10 gives us the 50. And again, the height of that triangle is still 100. So now that gives me 2,500. Forgot to label on this graph, this was 500, and the area under here is 2,500. And that's being added on to that 500. Again, it's a slope that is steep and gets less and less steep until it reaches 0. So it's a quadratic that looks a little bit like that, going up to a maximum amount of 3,000. And that 3,000 is coming from the 2,500 plus the original 500 that was below it. So that gives us a total distance, how far the car has traveled, of 3,000 meters. Just based on those graphs, just based on doing those integrations. Notice I didn't really have to do these integrations that we had over here. It wasn't necessary when we can just use those relationships between slope, between area of the curve, to go between these graphs.